I'm Piotr Wojciechowski, and I'm a software engineer, a senior software engineer at NVIDIA. I've been there 4 years. Prior to that, I was a student at this faculty. So I graduated my bachelor's degree, and I did my master's before I just went to the industry. And so I wanted to talk about inference optimization techniques. So you can probably start. So the talk content. So I wanted to talk about, first of all, I wanted to introduce the notion of inference and whether inference is actually a machine learning. Then I'll dive deep into inference, different kinds of inference optimization techniques. Further, I'm going to talk about some common benchmarking scenarios. And at the end, I'm going to try to answer the question if the GPUs are suitable for inference. OK, so is inference a machine learning? And so suppose inference is a machine learning. But so when you think about it, the inference is the part of deep learning when we calculate the function that our neural network represents. And during the training, we check the result against the reference and do a backpropagation of gradients to update the weights. So inference is easier in that terms that we only do this first step. So we never upgrade the weights. We assume that you have trained your network already, and you're not going to update it. You just want it to calculate the function that it represents. And so inference does not update any weights. So then inference is a machine without learning. So inference is a machine. It's probably not the best way to describe that. So yeah, I'm going to do a little bit of more basics. I'm sure most of you are already familiar with that, but there's a reason for that. I'm gonna use some of those notions that are familiar to TensorRT, but different frameworks, they have different definitions of each operators. And so what is deep neural network? It's a directed acyclic graph of some mathematical operators. In TensorRT, we call them layers. That take some input tensor and produce the output tensors. So in TensorRT, some of the layers actually embed internally a tensor, but you can also think about it as a different operation that, like an operator that takes additional tensor, a constant tensor, and that's what some other frameworks are actually doing. So yeah, a layer may embed weights. These are essentially additional tensors that I talked about. When we calculate the layer results in the middle of the network, the results of that calculations are known as activations. And the last layer's activations, we just call them outputs. So tensor here, it's just a high dimension matrix. That's probably what more math and computer science students are more familiar with. And each tensor has an associated data type and format. And so it's either FP32 or FP16 or even the integer values, as well as the layout in the memory that could be different. So this could be like a batch size channel height weight, or the order could be actually a different. So a batch size height width and a channel. And we can think of even more complex formats, such as the vector formats, when we actually stack 16 values of weights for each channel. And some common layers that are TensorRT using is convolution or deconvolution, all sorts of matrix multiply, so matrix vector multiply as well. We call them fully connected layer. There are activation layers, so ReLU, sigmoid, hyperbolic tangents, leaky ReLU, and all sorts of others. There's a softmax for probability distribution. There's all different sorts of flavors of tensor manipulation, so concatenation, gathering, slicing. There are element-wise operations as well, so an operation that operates on each element individually. And we have a scale layer that is an artificial layer. It's an optimization, essentially, that we combine multiple element-wise operations into a single one. And there's also a constant layer, which is just a tensor. We can think of it as an embedded tensor. It's a constant layer that's not going to change. And there are different kinds of there are other layers that I'm not actually mentioning. Well, I encourage you to take a look at it. Take a look at TensorRT to figure this out. And so I want to go into inference optimizations techniques. So what I wanted to talk about is 5 optimizations that like one of the most 5 optimizations that we are like proud of. We actually do. And so I want to talk about layer and tensor fusion. Also about kernel autotuning. Then I'm going to talk about multi-stream execution. I'm going to also mention the dynamic tensor memory and precision calibration just shortly. And so let's consider an optimized network graph that you can see over here. So it actually rises from bottom to the top. So first of all, we have a concatenation layer. Then we have an input. Then we reuse that input in 4 different ways. We apply the convolution bias ReLU, and then we merge the output into a concatenation layer, and that produces us a tensor that could be considered as a next input towards further optimization or next layers in the network. So what can we do about how to speed it up? And so when you think about it, it turns out that GPU architecture, the way we implement those layers is we start with actually having one kernel per layer, which is essentially, we can think of it as a function that actually loads the data, performs the operation, and writes the data out. And so over here, you load the data for the convolution, you apply the bias, then you write the data out. Then you have a bias layer that loads the data from the previous layer, applies the bias, which is an addition, and then writes the data to the GPU memory. And then you have a ReLU layer, which, again, loads the same data, loads the output from the previous layer, and then do the operation and write that back. And so when you think about it, one of the optimization that we can do is to fuse layers. And so we want to fuse convolution and bias and ReLUs such that we only load the data once, do all sorts of operations, and then write the data once. That saves us a lot of memory bandwidth on the GPU. And so that's a convolution bias. CBR stands for convolution bias ReLU operation. And this is the graph vertical fusion. Now, as you can see, there are 3 different one-by-one convolution bias ReLU operations, each operating as taking the same input. So we are loading the same data multiple times. Essentially, we scattered our computation into actually doing like computation like one part, second part, and the third time. Whereas normally, like what GPUs are good at is actually a huge chunk of data done once. And that would be a graph horizontal fusion. And so we have one-by-one CBR. And the last, there's another one, there's another optimization that I wanted to talk about. It's essentially, when you think about the concatenation layer, what it does is essentially the 3x3 CBR and the 5x5 CBR and 1x1 CBR's output, we write them somewhere in the memory, And we have a special operation called concat that loads the data again from the memory and writes it into a specific format. So how about we just write it in a specific format and eliminate the concat elision? We eliminate the concat layer, and that optimization is known as graph concat elision. So there's also somebody slacked us recently about the question whether, so suppose my network has more than one output, and I'm actually interested in getting to know what's the result of a very specific output, and I don't care about the rest. And I'm worried that because normally I can just run the inference on the whole network and discard the results that I don't care about. I'm just worried if the performance is going to be good. And we can actually modify, well, one thing we can do is just to modify the network and just rebuild again, and then just eliminate the outputs and do the engineering, and it seems like a lot of work. And if we have graph optimizer, if your software has a graph optimizer, it's essentially what we're interested in is removing unreachable nodes, and that's one of the optimizations that we do as well. So there's also like a case study that one of the DevTech engineers actually did for a customer. So yeah, the title is "Fixing Performance Limiters," and the problem that he wanted to solve is he wanted to have to speed up the collaborative filtering layers. And by that, well, the technique that he wanted to apply is essentially a fusing of the layers. So here's the network, essentially. So it takes users and some courses, has an embedding layers that actually encodes this. It concatenates those two tensors, and then it performs an MLP layer. That was essentially our inspiration towards including MLP layer as a first-class citizen for TensorRT 4. And so the MLP layer consists of matrix multiplication, followed by the bias, which is a matrix add, and sigmoid, which is an activation, element-wise activation on top of it. And so there were n layers, and then there's a final layer that just writes the output. And so when the DevTech actually profiled that, it turned out that running each layer separately, the algorithm was memory bandwidth limited. And when you think about it, the GPUs, well, the memory bandwidth rises, like the throughput of memory bandwidth on the GPUs rises much slower than the flops that GPUs can actually offer. And so it's if the problem is memory bandwidth limited, then you don't really have too much of an incentive of buying new GPU, because you will not get as good benefits as if this problem was compute bound. So it would actually depend on the theoretical flops of the GPU. And so the first thing that he tried is a layer fusion, which is gem plus bias plus sigmoid. And so he fused those layers. He still have n hidden layers. It's just each of those layers are fused kernels. And it turns out that the resulting blocks are still memory bandwidth limited. And so that didn't really help. And so the next optimization that was applied was to actually fuse essentially everything into a single kernel. And that turns out to be turned out to actually break break this problem from memory bandwidth limitation into a compute bound problem. And that's something that we love to optimize, because the next generation, the bigger the GPU, the better performance you're gonna get, and that's gonna come for free. Okay, another optimizations that I wanted to talk about is kernel autotuning. So suppose we have a wide selection of algorithms that implement each layer. We have a cuBLAST layer, we have cuDNN, we have even custom layers, custom algorithms that are provided in a binary format. We also have like a CUDA kernels that we own for those layers. And so we have wide selection of algorithms doing pretty much the same thing. Each of them has a different characteristics. So one is better at some tensor, some problems. The other one applies better for the other. And it's non-trivial to make an optimal choice that actually says this algorithm is going to be the best on a given output. And we didn't want to dive deep into that. So that's only for like a single layer. Then we have the layer fusion, and for the fused layers, we also have different tactics. So when you fuse the layer, you can implement it either one by one. You can either run the layers one by one, or you can actually run the algorithm that actually implements everything in one shot. And so these are like two different tactics, and it's not easy to say, well, we have intuition that the one that's fused is going to run better, but it's not always the case, and so we don't want to go deep into that. So there's also an issue because some of those tactics rely on the format of the tensors. So one implementation may require NCHW format, and the other requires NHWC. When you think about tensor cores, they require a vector format, which is yet a different flavor. And so even though I have an algorithm that implements my layer, perhaps it's actually beneficial to use a different one because the next layer is going to rely on the vector format that we may produce, and that's something we also care about. And so the question is how to choose the best algorithm for the whole network. So I'm going to try to describe it as a graph problem. So given bipartite, that's in Polish dwudzielny, graph, G with operators and the tensors. Given that each tensor we can assign a format to each tensor. So essentially, if I have a tensor, it has some sort of format. And if I have an operator, which is essentially a layer that computes one tensor, gets as an input one tensor and produces the other one. So each implementation, an algorithm, requires a particular format for inputs and produces particular format of the outputs. And each implementation may have a cost, which is going to be a time for now. We're not going to go deep into like memory requirements or any other stuff like that. So the problem for implementation is essentially how to choose implementations and format that minimize the total time. So how do I run my network? Like, what's the best combination of algorithms and formats that produces the fastest execution of the network? And when you think about it, it's a non-trivial issue. And actually, the one thing that we can think about is an easier problem when we say, okay, how about if we use one format all the time? If we use one format all the time, then it's starting to be a little bit more trivial. When you think about it, it resembles a single source shortest paths problem. So we can do some sort of like a dynamic programming. And what by that means is essentially, if I choose the best algorithm for each layer, and I combine those results, I think I can prove that we're going to get an optimal solution in total. So given a single format, it's easy. Given multiple formats, it's exponential, I guess. And so it's hard. So again, the network is a directed acyclic graph of layers, sorted topologically. And if we execute them sequentially one by one, that should essentially compute the whole network. As I said, many libraries have internal heuristics of which algorithms to choose based on input data. The CUDA has that. QBLAS has that. Many of the CUDA algorithms have that. And TensorRT took a different approach. So TensorRT, instead of making like a heuristic that works in general, we just try to optimize. For your target data, for your target hardware. And so we take an extra step for you. It's called autotuning, where we run wide sort of implementations on your hardware, and we perform the calculation of how long did it take each of the implementation, and we essentially choose the best one. So that's how we got in that way. Whenever there is a new algorithm coming up, we can just include it into the autotuner, and it's going to be considered by it. And if it's better, then it's going to be chosen, and it's going to improve the total execution time. So there's a nice. So essentially, TensorRT is a library that is built on top of CUDA, and it's meant to be for a GPU. So essentially, I'm going to talk about multi-stream execution and how that can actually help your problem. And so CUDA execution exposes computational coprocessors, or SMs, if you will, and that's only for manipulating data that are on a GPU. And there's also a DMA engines that they require. The purpose is to move the data between CPU and GPU. So one thing that many people find useful is that DMA transfers may overlap with compute. So we can actually run the computation and then prefetch data for the next layer, as well as write the data from the previous layer. So I'm going to give you an example of that shortly. And in throughput scenarios, that's going to be later. But when you think about it, if they overlap, then sometimes we can think of it as a hiding of input and output transfers behind computations. And essentially, CUDA streams is a concept that helps express such pattern. There's a new feature called CUDA graphs, that was introduced in CUDA 10. That's a different approach, and it's the complexity of that is beyond this talk. So if you're interested, I encourage you to take a look at CUDA graphs. Anyway, so streams and compute overlap. So suppose I have a toy problem. Suppose there are many cat images on the internet, and suppose I'm not a fan of cats, so I would like to change those pictures of cats into something that I like, for example, pictures of dogs. And so I have my cat on the CPU, and I want to have a dog on the CPU as an output, and I'm going to use a GPU to speed it up. So one thing that I can do is to divide this cat image into three parts. So head, a body, and the bottom. I can, by step one, I can move the data from the CPU, the head from CPU to the GPU. I can compute a dog head, essentially. And I can move the head of my dog back to CPU. So that's partial result, essentially. So these are three steps, and I'm going to do the same thing for the body, and the same thing for the bottom. And here we are. It's a picture of the dog. And so the question is how to make it faster on the GPU. And so suppose I do the copy of the head. I can do the computation of the changing the head of the cat to the head of the dog as well as in the same time, I can start prefetching the data, prefetching the body of cat to the GPU. So this is step 2, and there are 2 things happening at the same time. Step 3 is actually when we copy the data of the dog from GPU back to CPU, as well as we do computation on the body, and we prefetch the bottom of the cat. So there are 3 things happening at the same time. Then we copy the body output back to CPU, as well as we do compute of the bottom at the same time. And then we copy back. So 5 steps instead of 9. So I presume we're a little bit better than that. So there are up to 3 simultaneous operations happening at the same time. So we are copying the data, the output data. We are doing the computation, as well as we are prefetching the data, all happening at the same time. And that's something what GPUs are actually shining, because that way we can essentially hide those computations, hide the data transfers, and think only about the computation time. So when you think about the timeline, we are doing initially we are doing the copy, then we did the compute, and then we did another copy, which is so the first one was data transfer to the GPU. Then there was GPU doing the computation, and then there was data transfer back to the CPU. Now, what we did is essentially we did an overlapping of copy and compute. If you think about it, if you think about the notion of pipelining from computer architecture, that's essentially the same thing. So it sounds very like a trivial thing to do, and yet because CPUs are doing this for us, people apparently tend to forget about that. So this is essentially a software pipelining. And as you can see, the difference, there's a time saved essentially that we saved because we are doing the overlapping. And in more detail, that is exactly what has been happening. So first of all, we were copying the prefetching the head, then we were doing compute, then we were doing copy back, and this is essentially the same thing, but in the timeline. So I think it's a general idea, and you can think about how to actually do this for neural networks. It should be the same thing, essentially. Okay. So the next optimizations that I want to talk about is post-training precision calibration. So suppose we were training in FP32, so float. We are using floats as a data type, and for inference, we would like to use an integer values. So we want to use a smaller data type and perhaps faster hardware units to further speed up our problem. And so given the input images, we can do an FP32 inference, and what we can collect is an activations distribution. And this is like a histogram, and when we have that as our input data, we can try to use the same thing on int8, and we do such the calibration in such a manner that we minimize the relative entropy between the int8 outputs versus FP32 outputs. It's also known as KL divergence, and one of the students from University of Warsaw was actually working on that, Szymon Migacz. He has an excellent talk that is recorded from GTC 2017, as far as I remember. I encourage you to take a look at it if you're interested. So what we are given, essentially, the result of that is tensor dynamic ranges. They are symmetric. So essentially, given a tensor values, what is the multiplier that we apply to get the integer values? Or well, it's actually a division. So given integer values, how do I multiply them to get my FP32 results back, essentially? And so we do this per layer, so the convolution one and the Rayleigh one. And then we have a calibration cache. Then we write that down, this data, in those quantized values of that in a hex format. Okay, so next thing that I wanted to talk about is the common benchmarking scenarios. So suppose input tensors are on a CPU. This essentially, I'm trying to describe the problem. So suppose input tensors are on the CPU RAM, and we consider inference as being done once the output tensors reach the CPU RAM data back. We can use asynchronous work execution on the GPU, and we can consider that network computation is a little bit more complex than moving the data. So there are 3 different scenarios that I wanted to talk about. And so that would be minimum latency. What is the minimum latency for a given batch size? That's one of the problems. The other one is what is a maximum throughput for a given batch size? That's a different problem. When you think about it, latency could be considered as an inverse of throughput, but it's not necessarily the same thing. And the same algorithm may be suboptimal for the other problem. And so the third one that I wanted to talk about is what is the maximum batch size, given that I have a constraint. I, for example, serve users a web content, and I can't wait more than 7 milliseconds. So how many users can I serve at the same time, given that I want to give them results back in about 7 milliseconds, or n milliseconds. And so minimum latency for a given batch size. So the way we can implement that is essentially we can copy the inputs from the GPU memory to the GPU memory, run the inference on the GPU, copy outputs to the CPU memory. Easy. We enqueue operators above in a single CUDA stream, and we can actually use CUDA, a notion of CUDA events. So GPU can actually measure the timestamps, and so we can insert the timestamp when the GPU starts execution, and insert the timestamp once GPU stops execution, and measure the difference. That's essentially how much time did it take. So that's our latency. A different problem would be a maximum throughput for a given batch size. So as I said, one can use the same algorithm as for minimum latency, because one can think that throughput is an inverse of latency. So essentially what happens is we copy the data, run the inference, copy the data out, and we do this in a loop. Again, copy data, run inference, copy data. And can we do better than that? So that's the question. I'm going to try to answer. So as I've been telling you previously, we can use CUDA streams and the notion of compute and copy overlap. So we can hide DMA transfers behind computations. And essentially that problem, it translates into something like, if we had the GPU data on a GPU, we run the inference, and we had the data on the GPU, it's the same thing. Like, we have hidden the DMA transfers between CPU and GPU, and what matters is essentially the cost of running inference on the GPU. So that's going to give you a little bit better results than the inverse of a latency. And then there's the third problem that I wanted to talk about is a minimum latency for a given batch size. So we can copy inputs to the GPU memory, run inference, and copy. Same slide. Okay. A maximum throughput given latency constraint. Sorry about that. So we can run the throughput scenarios, and that essentially maximizes our throughput, but at a given batch size. But then one can think about the algorithm that essentially measures how long does it actually take for one input to migrate from CPU to the GPU, do the inference, and migrate back as a result to the CPU. So that would be our latency in a throughput scenario. We can measure that and essentially adjust the batch size accordingly. So if it takes too long, we can decrease the batch size. If we are okay within the limit, we can try to increase the batch size to essentially create more work for the GPU. And there's an interesting variant of that. If we only care about latency constraint 99% of the time, so suppose there's like 1% of results that are going to run a little bit more than 7 milliseconds, we may as well just don't care. And that's essentially, if we had this constraint, then we can consider a different batch size. Okay, so the question that I wanted to finish my presentation essentially is, are the GPUs suitable for inference? In other words, whether the work that I'm doing is actually meaningful. And so there's a quote from one of the websites that I was inspired that inspired me to do this presentation. It's essentially, for inference, CPU is recommended because there is no latency overhead between CPU and GPU communication. And that's it. Like, there's no problem statement. There's no data. It's just one sentence. And apparently everyone is okay with that. So yeah, I hope I was able to give you an overview essentially of inference problem. I hope I was able to define the inference and how this actually look into machine learning. I talked about inference optimizations. I talked about common benchmarking scenarios, and I asked the question that I didn't give you an answer, whether the GPUs are suitable for inference. So given that the TensorRT is a performance product, I have one slide for performance. So the scenario is throughput under 7 milliseconds of latency, and we were doing this for Tesla T4, which is a server-grade GPU that runs under 70 or 75 watts. So essentially, you don't need any cables. You just plug in. It's a plug and play, essentially. You plug it into PCIe, and it just works. And so there are three networks that we run the benchmarks. And what you can see is a non-linear speedup. It's actually a superlinear speedup. So it's much more than just linear. And there's a reason for that I'm going to try to explain it. And so as you can see, the FP32 inputs results are like, I don't know, within 500 for ResNet. FP16s are like 2,000 images per second. And int8 reach more than 4,000. And so what happens, essentially? Why are we getting more a superlinear speedup, given that our data shrinked twice, and we were using perhaps 2 times faster units? And so the reason we would not expect like a different than a linear speedup. So essentially, what happened? Essentially, and the answer is kind of like a complex. It's a vicious circle. So essentially, when we use a smaller precision, our data is smaller. Therefore, we can actually, the time it takes, a latency that it takes to move the data is actually lower. And so given the lower latency, we can try to increase the batch size. That gives us more data. And the more data that we operate, we can actually do more meaningful operations. We can extract more operations from it. And if that's faster, then we can actually try to increase the batch size. It's a vicious circle that actually is an explanation why we're getting a superlinear speedup. And with that, I want to thank you all for your attention, and thank you.